guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So when talking about the Lewis structures, I kept mentioning the importance of achieving an octet, because that gives any atom the most stable conformation. But there's three general ways in which this octet rule actually breaks down. Firstly, if molecules have an odd number of electrons. Secondly, molecules in which an atom has less than an octet. And thirdly, molecules in which an atom has more than an octet. And so I'm going to walk you guys through each of these different scenarios, and you'll see why these are exceptions. So the first one that I mentioned is having an odd number of electrons. So as an example, let's draw the Lewis structure of NO, nitrous oxide. So first, let's figure out the total number of electrons. And so for nitrogen, you have 5 electrons in the outer shell, and for oxygen, you have 6, and you have a total of 11 electrons. So already you can see that this is an odd total number. And so let's draw out the bonding structure, NO, and then octet on the outer element, so 1, 2, 3, 4, 5, 6. And the remainder of the electrons, so 11 minus 8, which equals 3, goes on the central atom. So 1, 2, 3. So there are currently 5 valence electrons around the nitrogen. So a double bond would place 7 around the nitrogen, and a triple bond would place 9 around the nitrogen. So in this case, there's an exception to the octet rule. Now the second case scenario, let's talk about when the central atom has less than an octet, so less than octet. So this is most often encountered with elements such as boron and beryllium. So let's note that down too, boron and beryllium. And so as an example, let's do the structure BF3. So as always, the total number of electrons is, we have 3 times 7 for the fluorine. And then for the boron, we have 3. And we end up with 24 electrons. So now see, it's an even number, but it's still an exception to the rule. So now let's draw the connections. BF3. And then add octets to the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then there's 19, 20, 21, 22, 23, 24 in the bonds. So when you add extra electrons to the central atom, you can't do that because you have 24 electrons minus 24 electrons, which you are allowed to distribute, and that's 0. But does the central electron have an octet? No, because it has 2, 4, 6 electrons instead of 8. So you can add a multiple bond or a double bond to see if the central atom can achieve an octet. So let's try that. B, F, 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 and now it looks like this. So now the central boron has an octet, right? However, in this structure with a double bond, the fluorine atom is now sharing extra electrons with the boron. So right here. And so the fluorine would have a partial positive charge, and the boron would have a partial negative charge because of this sharing. And this is inconsistent with the electronegativities of fluorine and boron. So again, if you look at the trends in the periodic table, you will see that the electronegativity of boron and fluorine don't match this interaction. Fluorine is a lot more electronegative than boron, so it should not have a slightly positive charge. Thus, the structure of BF3 with single bonds and 6 valence electrons around the central boron is the most likely structure. And so this one is less likely, and we actually end up with the one that we had before. But as you can see, the central boron has less than an octet in order to have its most stable structure. So now we'll talk about what happens when you have more than an octet. So finally, we get to more than an octet, and this is the most common example of exceptions to the octet rule. So PCl5, and this is a legitimate compound, looks like so. We have chlorine on both the top and bottom, and then like so. If we end up filling the valence electrons of the chlorine, it would look like this. Except your picture should be neater than mine because I'm rushing this picture right now. All right. And so the expanded valence shells are observed only for elements in period 3 and beyond. So I'll write that right here, period 3 and beyond. So the octet rule is based upon the available ns and np orbitals for valence electrons, where you have 2 electrons in the s orbitals and 6 in the p orbitals, as we talked about prior. And so beginning with the n equals 3 principal quantum number, since we go past period 3, the d orbitals become available. And the orbital diagram for the valence shell of phosphorus can be shown like so. We have 3s, 3p, and then we have 3d, like so. And so in this case, we're not showing the 1s and the 2s and the 2p. We're just skipping to the 3s. And so we would have 1, 2, 3, 4, and 5. So third period elements occasionally exceed the octet rule by using their empty d orbitals to accommodate additional electrons. So basically, they have this whole shell right here, the 3d orbital, into which they can actually accommodate additional electrons. So I'll write that down for you. And that's the reason for which they can expand their octet. And so another thing that we need to consider is size. So the larger the central atom, the larger the number of electrons which can surround it, which makes common sense. And so expanded valence shells occur more often when the central atom is bonded to small electronegative atoms such as fluorine, chlorine, and oxygen. And that concludes our different octet rules, the exceptions to this rule.